This is the second part of lecture 3, and in this part we'll learn about batch sterilization process. So if you want to use heat to sterile your media, you can do in two different way. Either you can use batch sterilization process or continuous sterilization process. So first I'll talk about the batch sterilization process. Okay, so the main aim of batch sterilization process is to attain the sterility with the least change in nutrient value of the media. Okay. However, in this regard, I mean, if you consider the media nutrient quality, continuous sterilization process is better than batch sterilization process in avoiding the damage of nutrients. So I'll talk about it later when I will talk about the continuous sterilization process. In that time, I'll explain it. I mean, why continuous sterilization is better than batch sterilization process in avoiding damage of nutrients. Anyway, in batch sterilization process, the maximum temperature which is possible to use is 121 degrees Celsius. Okay, and high temperature and short time sterilization attained by taking into consideration the heating and cooling time of the batch sterilization. Okay. Anyway, whenever we want to use batch sterilization process, we have to consider some points. So these are those points, like how much temperature of the fermentation media is increased during heating or decreased during cooling periods of the batch sterilization. Okay, so and then the initial number of microorganisms in the medium and the thermal death rate of the selected organism. So we have to consider these 3 points during designing our batch sterilization process. Okay, now in batch sterilization, we'll use heat to reduce the contaminant microorganisms. Okay, and we can use this heat. I mean, we can use the heat in batch sterilization process by different mode, such as by direct steam sparging, or by electrical heaters, or by circulating constant pressure condensing steam through heating coil or jacket. Okay, and the cooling the medium is carried out by sparging the steam through the cooling coil or jacket. So if you look at this cartoon figures, it shows the different mode by which we can do the batch sterilization, such as, for example, one mode is we can directly sparge steam into the media. Okay, and this steam, when it will mix with the media, it will sterile the media. Okay, or we can achieve the heating by using electrical heating system, or we can use steam heating. Okay, so in case of steam heating, we will not directly sparge steam into the media. Rather, the fermenter that we need to, I mean the fermenter that we need to sterile, or the media will be inside the fermenter, and the fermenter, it will be a jacket. There will be a jacket, and inside that jacket we can supply or circulate steam. Okay, so when the steam will circulate in the jacket, they will sterile the media inside the fermenter. Okay, so these are the 3 different methods by which we can do batch sterilization. Okay, now when running a thermal batch sterilization, I mean, when we do sterilization using heat in a batch sterilization process, the system goes through 3 steps: heating, holding, or cooling. Or in another word, you can say that the batch sterilization process, okay, it has 3 steps: the heating step, holding step, or cooling step. Okay, and the temperature is I mean, when we do the batch sterilization, we increase the temperature, and the temperature is increased until it reaches the sterilization temperature, where it is held for a set of period of time, and this is called holding period. Okay, so we first increase the temperature until to our set value. Okay, that means, so suppose we want to sterile at 121 degrees Celsius, so we'll increase the temperature until 121 degrees Celsius, and we will keep that temperature for some moment. This is called the holding period. Okay, and during this phase most of the unwanted microorganisms are destroyed. That means most of the contaminant microorganisms will be destroyed during the holding period, and then finally, the holding period is done, then the system is cooled to bring the sterile media back to the desired temperature. Okay, and as I already said that the batch sterilization process, it has three steps during the heating, like the heating step, holding step, and cooling step. Okay, and the destruction of microorganisms, it occurs in all these steps like heating, hold up, and cooling. However, most of the destruction occurs during the hold up period. Okay, anyway, although most of the microorganisms they get destroyed in the hold up period, but actually when we'll uh, calculate the time required for batch sterilization, we need to consider the destruction of microorganisms of all these steps, that how many microorganisms get destroyed during the heating or hold up and cooling period. Okay, so we'll consider all these steps and then we'll set the time that for how long we'll do the sterilization. Okay, so now when we need to do this kind of calculation, that means suppose we want to uh, calculate that how much time we will use for the holding period. Okay, so first is we need to calculate the del factor. So how we can calculate the del factor? By using the equation of del factor. So we know that del factor is ln n0 by nt, right? Ln n0 by nt. Now say suppose we know the ln 0, ln n0. We know the n0. N0 is the initial number of microorganisms. So what will be the nt? Nt is the number of microorganisms after the time t. Here t is the time, t is the exposure time. Like if we use heat for 10 minutes, then t will be t will be 10. Okay, anyway, so we know the initial number of microorganisms n0. So for example, you are dealing with a fermentation process. You want to sterile the media, and you calculated that your unsterile broth contain 10 to the power 11 viable organism. Okay, so this is n0. N0 is 10 to the power 11. So what is nt? Okay, in industry there is a accepted range that we will accept if this amount of contamination is there, and usually the most adopted accepted range is we allow the contamination of 1 in 1000. Okay, so that means this is the nt. In 1000 only one microbes will be there. Okay, so that means the nt will be 10 to the power minus 3. Okay, as this is the accepted value of contamination. Okay, so thus we have the n0, which is 10 to the power 11. We have the nt 10 to the power minus 3. So then we can easily calculate the del factor. So del factor will be ln 10 to the power 11 divided by 10 to the power minus 3, so which will be 32.2. Okay, so now this is the del factor. Okay, so if the initial number was 10 to the power 11, we need the del factor 32.2. Okay, so now we already saw that during batch sterilization process it has three steps: heating, hold up, cooling. So we also know that cell die in each of these steps. So if we want to calculate the total del factor, which is called overall del factor, we have to consider del factor of all these individual steps. In fact, that is what we do. Okay, so like when we calculate the overall del factor, we actually just add the del factor of all these individual steps, such as, so that means we can represent the overall del factor by this equation. So del overall will be del heating plus del holding plus del cooling. Okay, and by using this equation we can calculate that how much del factor will be required in the holding period. So if we can get this value, I mean if we can get the value of del factor del holding, then from that we actually can calculate the time, the holding time. Okay, so how we can do that? Okay, I will see in the next few slides. So first, okay, say for example from this equation you want to get the del of holding. So del of holding will be del overall minus del heating minus del cooling. Okay, now let's do some math to understand it more clearly. Okay, so say the overall del factor is 32.2. Okay, and the heating del factor is 9.8 and the cooling del factor is 10.1. In that case the holding del factor will be overall del factor minus heating del factor minus cooling del factor. So in this example the holding del factor is 12.3. Okay, now from this del factor, holding del factor, we can calculate the holding time. How? We know that del is equal to kT. Okay, and the scientist Mr. Dendorfer and Humphrey, who propose the del factor, they calculate the specific rate of Bacillus stereothermophilus, and we know that Bacillus stereothermophilus spores are more stable. So we can actually use the value of or death rate of Bacillus stereothermophilus as a test value or indicator value and use it to calculate the holding time. Okay, and they calculated the specific death rate of Bacillus stereothermophilus spores at 121 degrees Celsius as this 2.54 per minute. So 2.54 is the specific death rate of Bacillus stereothermophilus spores at 121 degrees Celsius. Okay, so if we use this value in this equation, then we can get the value of small t, and this small t is the holding time. Okay, so in this way, by using the equation of the del factor and using the equations of del factor, we can calculate the time required for hold. That is, we can calculate the holding time for our batch sterilization process. Okay, now say you are using you want to set the batch sterilization process for your final fermenter. Okay, so how we do that? So we need to optimize the value, that we need to optimize the holding temperature, holding time, and also the temperature for our process. But we know that the final fermenter, they are big, so we just cannot do this study. We just cannot do the optimization for our final fermenter. So what we do the optimization using the pilot sterilizer, okay, or the pilot sterilization, and then we can scale it up, okay, for the bigger fermenter. Okay, or think about this one. Say for example you want to sterile a large volume of media, so that using batch sterilization process, so you need to use a very large vessel for that. Okay, so now you just cannot do all the optimization using that very large vessel. So in practical, what we do, first we optimize the process using a smaller vessel, which we call pilot sterilizer, and then we just scale up the parameters for the final large fermenter. Okay, so how we can do that? Consider this example. So for example, if a pilot sterilization were carried out in a 1000 dm³ vessel with a medium containing 10⁻⁶ organisms per centimeter cube, okay, requiring a probability of contamination of 1 in 1000. 1 in 1000 is the accepted value. Okay, so from here we can calculate the del factor. The del factor is ln n0 by n2 n0 by nt, and the value is final value will be is 34.5. So this del value of del factor was calculated using the pilot sterilizer. Okay, so now we can actually scale it up for a bigger sterilizer. For example, if the same probability of contamination were required in a 10,000 dmq vessel using the same media, so what will be the del factor? So in that case, we can just calculate the del factor in this way. So del will be ln n0 by nt. The value of nt will be fixed because 1 in 1000 is the accepted value of nt. Okay, so only the value of n0 will be changed. So in that, here the size of contamination was 10 to the power 6 per cm3. Okay, so 10 to the power 6 into cm3 will be here. Okay, now we just have to multiply it with the volume of the final vessel. Okay, the final sterilizer. Okay, so which is 10 to the power 4. Okay, so then just calculate and you will get the del factor for your large sterilizer. Okay, so thus using this equation we can scale up the batch sterilization process. Okay, now the methods of batch sterilization. We observe the mode of batch sterilization. Okay, these are kind of same. Okay, so the mode of batch sterilization is whether we do it by direct or electrical heating or steam heating. The method refers something different. Okay, so the method means, well, let me explain first. So there are basically two methods of batch sterilization. One is in situ. Okay, that means we'll use in the fermenter vessel. Okay, the sterilization will be done in the fermentation vessel, or we can use separate mash cooker for sterilizing media. Okay, so this photo, the method of heating, these are the in situ sterilization method. Okay, so because we are whatever mode we are using, direct steam or electrical heating or steam heating, all we are doing in the fermenter. Okay, so that means in situ. But in case of separate mash cooker, we'll use a separate vessel to sterile the media, and then we'll supply this sterile media into the fermenter. Okay, now using separate mash cooker for sterilization have both some advantages and disadvantages. Okay, so first, the advantages of using separate sterilization vessel. So if we use a separate sterilization vessel, we can use one vessel for several fermenters. That means we can sterile the media in one vessel, and from that vessel we can supply the sterile media into different fermenter. Okay, so if we do that, it will save us some time. Okay, because we don't have to sterile the fermenter every time. Okay, we don't have to before the fermentation, so we just can do the sterilization of the media somewhere else. Okay, and then can feed the fermenter with the sterile media. Okay, another advantage is if we use a separate vessel, we can sterile the media in a more concentrated form. Okay, so the basic is we'll sterile more concentrated media, and then we'll dilute them using sterile water, and then we'll supply this media into the fermenter. Okay, another advantage is that in some fermentations, so the media is at its most viscous during sterilization. So in this kind of fermentation process where the media is very viscous, if we want to do the in situ sterilization, we need to use agitation, right? We actually have to use a very powerful motor to agitate the media properly to achieve a successful sterilization. Okay, so now if we want to have to use a very strong motor, it will it will be costlier, right? And also it will may cause more shear forces, which will be damaging for our fermentation process. So now we can avoid this problem by just doing the sterilization in a separate vessel. Okay, so if we can do the sterilization in a separate vessel, in that case we don't need to use a very strong motor in our final fermenter. Okay, so rather we can substitute the strong motor with a less powerful motor. Okay, and finally, uh, as we are doing the sterilization in a separate vessel, we can spare the fermenter from corrosion. Okay, because we know, I mean, high temperature, if the temperature is high, there is more chance of corrosion. Okay, so if we have to do the sterilization in situ, the temperature inside will be very high. It may facilitate the corrosion. But if we use a separate vessel for sterilization, for sterilizing the media, then we don't have to achieve, I mean, we don't need to put the fermenter into, I mean, we don't have to expose the fermenter with high temperature. Okay, thus we can save the fermenter from getting corroded. Okay, okay, these were the advantages of using separate sterilization vessel. Now the disadvantages of using separate sterilization vessel. Now, constructing a separate vessel for sterilization is costly. Okay, and then if we use a single vessel for sterilization and want to supply several fermenters from this single vessel, a lots of complex pipe work will be necessary. So thus this whole system, they will be I mean, there will be a inherent dangers of contamination, because there will be lots of piping. Okay, so contamination can comes from any piping, and if any piping, I mean, anywhere in the piping system there is some leak or damaged, the whole system can get contaminated. Okay, and another disadvantage is, if our our sterilizer fails due to some mechanical failure, we have to shut down the whole plant, right? Because we are using separate vessel to supply sterile media to all the fermenters. So if that vessel itself get failed due to some mechanical failure, we have to shut down the whole plant. Okay, now we can sometimes, I mean, accident can happen, so we can have some provision of contingency, right, which is called contingency plan. But you know, if we have to I mean, if we have to have some contingency equipment, it will again increase the cost. Okay, and sometimes that cost can be very much, so as much that we cannot actually have any contingency plan. Okay, so that was all about batch sterilization. In the next part, we learn about continuous sterilization process. So thank you for your patience.